Okay. So today we are going to continue our study of dynamic programming. We have so far looked at two examples. We looked at the longest common subsequence. We looked at weighted interval scheduling. So today we are going to look at two other problems, and we are going to do some more examples. Next class we will do a few more examples before we start our next segment on shortest paths, which actually uses ideas from both greedy algorithms and dynamic programming. So you're going to get a review of all of these as we go further in the course. Yes?
Is dynamic programming on the midterm next week?
Dynamic programming would be on the midterm. So let's look at all the ingredients of a dynamic programming algorithm. So the ingredients of a dynamic programming algorithm problem is first you identify some kind of optimal substructure property. And loosely what this is saying is that an optimal solution for a problem contains within itself optimal solution for subproblems. Okay? So, optimal solution for an instance contains optimal solution for subinstance. And you try to look at its optimal solution, you try to understand, oh, is this part of an optimal solution? If it is part of an optimal solution, what does the remaining solution look like? And then you can argue, oh, the remaining solution is actually nothing but an optimal solution for a subinstance. Okay? We have done a couple of those, we will look at two more examples. And then you can, the next step is looking at it, you can then translate this to a recurrence relation. Okay? And the way you develop this recurrence relation is you identify a small piece of the problem. Is this part of the solution or not? In a greedy algorithm situation, you can make the case that, oh, this is part of an optimal solution. Here you cannot. And then you consider, oh, if this is not part of the solution, what are the options? So then you will have a bunch of different options, and you write a recurrence relation that basically tries all of those options. Okay? The recurrence relation, you can also, by nature, recurrence relations are recursive, right? So you have a notion of a recursive structure here. But you're not going to do plain recursion, because if you just do plain recursion, that's an exponential block. So from here you want to be able to translate that into an algorithm. So the third component is figure out how to implement that recurrence relation as an iterative algorithm, or as a recursive algorithm with memoization. Implement as iterative algorithm. And to do that, you have to figure out the right order in which you're going to do things. Okay? Or as memoization. Okay? The fourth piece, these are basically the main pieces. After that, there are a few things you need to be able to do. Sometimes we write the recurrence relation in terms of the cost of the solution, and then because it's easier to write the recurrence relation as the cost of the solution because it's the sum of two things or maximum of some things. So the recurrence relation you often write it for the cost. So all of this is building the optimal cost. But from that you want to extract the solution. You can, from the very beginning itself, you can maintain and develop the solution, develop your algorithm in terms of extracting the solution. But sometimes it's easier not to worry about the solution, just worry about the cost. And then go on to extract the solution by making some changes to the algorithm. So I'm writing that as the fourth step. Adapt the algorithm to return solution, optimal solution instead of just optimal cost. Yes.
Professor, can we implement any recursive algorithm with the dynamic programming algorithm, like combining problems with
Good question. So the question is, can a divide and conquer, can we implement any recursive algorithm as a dynamic programming algorithm, or in particular is the divide and conquer paradigm like a dynamic program? And the answer is sort of yes, except that so a divide and conquer problem is a recursive problem. It's a recursive algorithm, a divide and conquer algorithm. And as we said, the dynamic programming algorithm also can be written down as a recursive algorithm. Okay. The key differences are, in some sense, you could think of dynamic programming as a sort of a broader concept. The key differences are, in a divide and conquer procedure, the recursive pieces are on completely non-overlapping pieces most of the time, except if you remember there were questions where you have overlapping problems, but most of the time they are not overlapping. Okay, that's typically the definition of divide and conquer, that you're dividing it and then conquering. Okay, while dynamic programming, by definition, the sub-pieces, sub-instances overlap significantly. Consequently, if you just do the standard recursion, it will give rise to an exponential blow-up. So you will have to do a recursion with some careful memory. Yes?
Just to entertain this question a little bit longer.
Yeah.
Maybe not for all cases, but take a classic case where the runtime would be, say, t of n over 2.
Yeah.
I don't know if this would exactly be dynamic programming, but if you take this concept and you basically just run one half of a symmetric tree, multiply that by 2, then wouldn't that be saving some order of half the cost?
So it depends upon the problem, and if I guess your question is, if you were to divide the problems down into halves
Or symmetric trees.
for a symmetric tree. So if you had a tree and you divide the problem into two parts, if you're able to solve the problem by dividing it into two distinct and separate parts, then calling it dynamic programming is sort of overkill. It's purely a divide and conquer thing because you've been able to separate the problem out into distinct pieces. All of the problems that we have covered, and the ones that we're covering today, you will see that it's difficult for us to be able to split the problem into equal pieces or divide it into. So,
Right, and I guess really my question is, would that save time? If you just
yes, if you were able to divide, most often that will save time. Whether it will work is a separate question. It may not work at all. Okay. Yes?
So, still, what's the difference between the optimal solution and
Okay, I'll show it with examples. So there is this step is not needed in some sense. If you have done 1, 2, 3 in a proper way, it's not needed. But often it's easier to write the recurrence for the cost as opposed to the solution. So it's the same thing as, are you asking me to find the optimal, the optimal size of the optimal knapsack set? Or are you asking me to find the optimal value of the knapsack? Okay. So, but it will become clearer in a minute. Okay. And then the fifth part is you want to be able to analyze the running time. Okay. I have not explicitly written down proof of correctness, meaning ideally, we won't be insisting this all the time, but ideally, when you write the recurrence relation, along with that, you should be able to prove that your recurrence relation is indeed correct. Okay? But if you have the right recurrence relation, that covers everything. So, as I have emphasized many times, this is really the crux of your algorithm. The recurrence relation captures everything of interest that is going on. Yes?
One last question.
Yeah.
If you're looking at these problems, what is a good way to like figure out when you're going to get overlap? Because that's the big thing
Yeah.
about this. Right?
Yes.
You need to identify this overlap. So
Yes.
if someone were to like, tell me a question in some instance, how could I say, okay, there is going to be overlap?
Yes. It's I think as in all things related to algorithms, there is no recipe. There are only some sort of hints and guidelines that you can extract from it. So the way to see whether this is a dynamic programming problem as opposed to a greedy algorithm problem as opposed to a divide and conquer problem, the general strategy is, can you take your problem and divide it into 2 parts or 3 parts and believe that if you solve this properly, if you solve this properly, there is a way for you to put it together. And that's the first thing you could try. And how do you know whether it fails or succeeds? You will have to play with some examples and see whether it succeeds or not. If that fails, then you have a sense that maybe divide and conquer will not work. Then you see, oh, does it have a substructure property? Is it the case that if I know that this is part of the optimal, is the remaining problem just like the same? Then if it is, then you have 2 possibilities. It could be a greedy choice or it could be a dynamic program. So then you check, oh, is there a specific choice I can make right now that will work? If that you're able to argue, then you go to the greedy algorithm. And if that doesn't work, then you see that you're not able to figure out locally you're not able to figure out what to do right now. So then you go to the runtime. In general, greedy algorithms would be faster than dynamic programming algorithms. This is just a vague statement, but yes. And divide and conquer algorithms would often be faster than dynamic programming. Divide and conquer and greedy, they're probably about the same depending upon the problem. Okay, so let's do our problem. This is a classic problem called the knapsack problem. And it's a clean problem where you're given n items. Each item has weight wi and value vi. Okay? And your goal, and you're also given a knapsack. Of weight W. Okay? So literally think of these items have certain weights, and each item has a certain value, and you want to put in as many items as you can in your knapsack. Okay? Where of course the main limitation is you have a weight bound, so you cannot carry more than this much weight. But what would you like to do? You would like to maximize the value of whatever you have picked.
This is not fractional, right? You have to pick
Correct.
one
Good. So a similar problem we saw in a station. Here you have to assume that all of these weights, you'll assume that all of these are integers. Assume they're all positive integers. All positive integers. Weight is a positive integer. And when you choose an item, either you choose all of it. Imagine this as, I don't know, you're a thief trying to store everything in your store, steal some paintings from a museum and putting everything into this knapsack. You can't. There will be no value in splitting a painting, so either you take the whole painting or you leave it alone. Okay? And you have a truck that can only carry so much weight. Okay? Okay. So, is the question clear? Okay. So certain things, just to play around with this problem, the thing that you note here is, of course, if the weight of all the items were equal, what would you do? Okay. Start from the most valuable and keep going down, right? Okay, so that's like a greedy algorithm. Okay, sort of the most simplest greedy algorithm you can think of. You just take the highest value element, put it in, then the next value element, then the next value. That's easy. Okay. What if all the items have the same value? Okay, there also it seems like the right thing to do is everything has the same value, then you want to take away as many items as you can, so you put the most value. Good. Okay. So, okay, so you want to favor high value. And low weight. Okay? So, if that's the case, this suggests an algorithm, a greedy algorithm, right? What's a greedy algorithm you could choose? You could choose, when you want to favor high value, you want to favor low weight, so you could choose something like, value minus weight. But that's strange. You will see that some heuristic like that won't work. But there are natural other heuristics you can think of. The thing would be pick items in order of decreasing order of. Okay, this is a greedy algorithm. Okay. Now, you could. There was a question as to how can I tell whether this is not a divide and conquer algorithm? If you were to treat it as a divide and conquer algorithm, you might say, all right, I'm going to split the n items into two parts, and maybe I want to split the knapsack into two parts. I'm going to use the first n over 2 items to fill in the first half of the knapsack, the second n over 2 items into the second half, and you can see that this is not a good idea, right? Because how do you split the n over 2 items? You might just, the first n over 2 items might be of very low value, and you're trying to fill your knapsack with that very low value, right? So you can play around with such ideas to see that the divide and conquer strategy. It's difficult to divide the problem, split it into two of equal size. Okay, So this is a pretty decent greedy heuristic. So, but before we get into that, let's try to see whether we can establish some kind of optimal substructure property. Okay. So again, optimal substructure property, what does it mean? It means that if you look at an optimal solution for a particular problem, and let's suppose this is the optimal solution, then if you maybe take out an item or take out some piece of it from the solution, then the remaining is an optimal solution for the remaining problem. Okay, so let's try to understand. So let's say you had this is your knapsack. Okay, and let's say the knapsack has these items: item 1, item 5, and I'm just placing them in increasing order of their indices. Okay, item 6, item 9, 15. Let's say these are the items that are there in your knapsack. And let's say you had a total n was 30. Okay? And I told you that this was the optimal solution. Okay? And this is the weight. The weight is some W. The weight of the whole knapsack is W, but the weight you might have filled up could be smaller. We don't know. Okay? Okay. So if this is an optimal solution, I want to make some claim about, is this also an optimal solution? So the question is, what is this? If this was, what can you say about the remaining solution? Okay. So let me call this solution S. So suppose S is optimal for my given instance. What is my given instance? It has n items, right? So let me write down S is optimal for the given instance with n items, for items 1 through n. And knapsack weight okay. What can I say about S minus 1? So, you know what this means? I'm saying that take a look at the solution S and remove this first item. Can I say that this is optimal? For what set of items can I claim that this is optimal? Wait, yeah.
Till the element before that, n minus 1.
Well, remember, so to the element before that, this is the element number 1. Okay, I've already included it in the solution. I want to know what is this. When I was trying to solve the problem for this, what elements was I considering? 2. I'm not allowed to consider 1 because 1 I've already picked. So I was looking at all elements between 2 and n. In this case 30, but 2 to n. And what weight was I allowed to include? The weight minus W minus the weight of 1. So I would like to say that S minus 1 is optimal for for 2, 3 until n, and weight w minus w1. It had better be, because if this is not an optimal solution for that remaining problem, then you can replace it by a better solution for the remaining problem and get a better solution than S. So that's the argument. So we don't even have to say much more than that. Why? If this whole thing is optimal for 1 through n and weight w, then this is optimal for 2 through n and weight w minus w1, because otherwise if there is a better if S prime is better, then if you add 1 to S prime, that's better than S. Okay? Contradicting optimality of S. This is the optimal substructure property, at least one piece of the optimal substructure property. Okay? Notice that even though I wrote this out in terms of examples here, this statement has no examples. This is a perfectly formal way to write this whole thing. Okay? All right? Is this, yes?
How do we know off the bat that, for instance, 1
Is there or not? Good. Good. So there it is an example. You're right. Thank you for catching that. So if 1 was sitting here, then you could make the statement. Okay? So suppose S is optimal and 1 belongs to S. Okay? But that's an excellent question. What if 1 does not belong to S? Suppose S is optimal and for items and 1 does not belong to S. Then what can you say? Okay, suppose S is optimal and 1 was not there at all.
And S is also the optimal for 2 through n.
Then S is also optimal for 2 through n. With what weight? Same weight W. Then F is optimal for items 2 through n. Obvious, right? If 1 did not get included when you are looking at all the items 1 through n, then of course if 1 was removed, 1 will not be included. There's nothing to do. The remaining has to be optimal. If it was not optimal, same argument. If S prime is better than if S prime is better, then S prime is also better than S for the original problem. Okay? So this is our step 1. You've identified this optimal substructure property. We've identified that if you give me an optimal solution, then I can look at an element, it's either there or not there. If it is there, then I know what the remaining problem is. If it is not there, then I know what the remaining problem is. In both cases, we are starting from a problem 1 through n down to 2 through n. So this is what it means by sub-instance. We've gone from a bigger problem to a smaller problem. Okay? What was special about 1? The point was 1 was any element. So you can just order the elements arbitrarily and the statement continues to hold. There's nothing special about 1. Okay? Now you might want 1 to be special. You might say, all right, maybe let me see whether a greedy choice works, and we do have a greedy choice there. And playing around with the greedy choice, if the greedy choice works, then in addition to this, you will argue, oh, if 1 is chosen so that it has the highest ratio of value over weight, then it is going to be part of an optimal solution. That would be your greedy choice property. So the second step would be to try to prove a greedy property. Element item with largest is in sum. Okay. And I will leave it to you because there are simple examples that show you this is not true. Okay. And the examples come about because you cannot break the items. Okay. There might be a slightly higher value item that might fill sort of part of the knapsack, just leaving no room for anything else, while there might be a better way to fill the whole knapsack with slightly less value. Okay. I'll let you, yes.
So generally, when you are trying to decide if to use greedy or non or DP, do you usually do it with examples?
That is the best way to do it. So firstly, you have to come up with so the question is, how do we decide between greedy and dynamic programming? The thing is, once you have established this property, to see whether the greedy property will be greedy, there is a greedy algorithm, you have to think about some greedy choices. And there is not obviously one greedy choice. Depending on the problem, there may be multiple greedy choices. So one approach would be you take a greedy choice and you try to prove that it's part of the model. And if you're struggling, that means there might be a bad example. Or you play around with some examples and see whether the greedy choice property is part of an optimal solution. Yes?
So using greedy algorithm, we
Yeah.
will find optimal solution. But using DP algorithm, we can find all the optimal.
No. So the question was, using greedy algorithms, can we find, maybe you will find one solution. Using DP, can you find all? The answer is, in general, no, because there could be many optimal solutions. And DP also, the way we would write it efficiently is it will pick one optimal solution among many. If there are many, it might just pick one. You cannot, in general, you cannot enumerate all optimal solutions. For the vast majority of problems, you cannot enumerate because there are just too many of them. Yes?
So in greedy, we were taking both the parameters into consideration, the
Yeah.
value and the weight.
Yes.
In this dynamic programming, we haven't mentioned value anywhere.
Well, we are mentioning the value because whenever we say optimal, what is the definition of optimal? It has the highest value. So when we say better, that means it has the highest value. All of this will come up when we try to write the recurrence term, okay, which we are going to try to write it right. Okay. Okay. So this was our step 1. Well, step 2 is now we want to write a recurrence. And again, what is the recurrence? What is the recurrence mean? We are trying to. The greedy property would have told us which element to pick, and here we do not know. So what we will do is, in order to establish the recurrence, we will have place the items in certain order. It doesn't matter which order. We're just numbering the items 1 through n. And let's say we define this opt. Okay, this is the optimal. So let me define it. Opt of I equals the value of optimal knapsack. Let me call it opt value. Opt value I is the value of optimal knapsack for items 1 through I, assuming knapsack weight W. Okay, value of optimal knapsack for items 1 through I, assuming knapsack of weight W. Okay, so remember what we have done. What do we really want to return at the end? You want to look at all the items 1 through n. So I should be n. What's your weight of your knapsack? Capital W. So I'm replacing it by little w. So I'm making these two as variables. Okay. All right. And notice one thing. I've written I'm just focusing on the value of the optimal knapsack. I'm not looking at the actual contents of the knapsack. Okay. This is related to this part. I could directly look at the contents. It's not a problem. I'm just writing it because it's a little simpler to do it this way. Okay. So the idea here is we will basically ask the question: is item I part of the optimal solution or not? If it was a greedy algorithm, I could have probably made the choice. But here I don't. I don't know. But I know that in either case, I know what to do. If it was part of the optimal solution, I know what the remaining should look like. If it was not part of the optimal solution, then I also know what it looks like. Okay? So let's see whether we can write the recurrent down. Opval IW. Okay? So let's do the base case first. So the base case is if, let's say, I was 0. So there were no items at all. So what will be the optimal value of your knapsack? 0. The other base case would be if the knapsack weight was 0. In that case, what will be the value of your knapsack? 0. So this is 0 if I is 0 or W is 0. That's easy. Okay. So now is the crux of the remaining thing. So what I'm going to ask is, I'm going to reduce my problem. Here I notice I reduced the problem 1 to n to 2 to n. Okay? And I'm writing there in the reverse direction because it's easier to talk about the reduction from n to n minus 1 and so on. Again, it doesn't matter. You can write it both ways. It just doesn't matter, but this is more convenient. So I'm asking the question, is I part of the solution? Okay? Again, we don't know. So we'll try both possibilities. If I is part of the solution, what is the remaining problem? So if I is part of the solution, then we need to solve the remaining problem optimally. But my value, I have to add the value of I, but I have to reduce the weight of I from the remaining problem. So if I is part of the optimal solution, my value would be Vi plus opt of I minus 1, and then the weight W minus the weight of I. Okay? But this is, I don't know whether this is really the right thing to do because I don't know whether I should pick I. The other option is I don't pick I. Then what is the remaining problem then?
I minus 1 W.
After 5 minus 1. Then what do I do from here? I take the maximum. That's it. That's the recurrence. And once you have this, in my opinion, we are basically done. Okay, now the couple of things. One is, notice that this is only capturing the values, right? It is not capturing what items to take. So when you write this we will implement this as a recursive, as a iterative procedure. At that time, we know what to do, right? If this turns out to be the maximum, then what should you do? You should include I. If this turns out to be the maximum, then what should you do? You should not include I. Okay? So we will keep track of those things when we write the code. Okay, so okay, so we'll just convert that into an iterative procedure. I is going to vary from. So first we want to make the base case. So when I is from 0 to n and up valve of I 0 0 for w equals 0 to w of valve of 0 w 0. So those are the two base cases. And then I'm just going to do a for loop from I going from 1 to n and little w going from 1 to capital N. So I going from 1 to n for little w going from 1 to capital W. What do? I pick the maximum of the two, right? Maximum of here plus of yes.
There can be duplicates.
And when you're asking duplicates of items in the same item may appear 2 times, yes. There's nothing preventing it. We are not allowing you to take 2 copies of the same element. Okay, each element is either taken or not. But 2 items may look the same. That would be fine. We are not sorting or anything like that. Okay? Any other questions? Yes?
Excuse me, on the top board in the lower right-hand side, is
Yep.
that I greater than 0 and W greater than 0?
Yes.
Okay, thank you.
Because if I was 0 or W was 0, we will just go to the base case. If both of them are positive, then we run this. Okay? Good. So, what do we want to return finally? Of value of n W. Okay? But remember, we really wanted to calculate the optimal set, not just the value. So what fixes do we do? Okay? So the best way to do it is to do what we did before. That is, we will keep track of what we ended up doing at each of these points, and then we will backtrack. Okay? So let's try to see how we will implement in this case. So there is nothing here. We are not taking anything. Here we are deciding whether we took I or not, right? If we took this, if this was the maximum, then we took I. If this was not the maximum, this was the maximum, then we took I. Otherwise, if this was the maximum, then we did not take I. Okay? So the way we will let me call that. Let me introduce a new thing called track. just write that down. If, and I'm writing it a little informally, but you'll get the idea. If this is maximum, then you will say, we will note that in order to let me explain that with a table. So this is I going from 1 to n. This is W going from 1 to W. Okay? I going from 1 to n, W going from 1 to W. And when we fill in a particular entry, IW, this is I, U. We are looking at two entries. One entry is, both the entries are in column I minus 1. One entry is at this location, the same location, and the other entry is at this location, which might be, so this is W, this is W minus W1, right? So we are comparing two entries, this entry, so if this is, and we are comparing this entry, adding it to the value, and we are picking the maximum and putting it there, okay? So if you put it there, if this is the maximum, then we basically make a note here that I not selected, okay? And we have to go here. If this was the maximum, then we make a note here that I is selected and we have to go here. Okay? So now when we want to calculate the solution for Wn, there it will say, are we taking the nth element? Yes or no? If it is yes, then we include it in our solution. If it is no, then we don't include it and you move here. So you basically just backtrack, and each time you're deciding whether you want to take the element or not. And it will be just one walk through this table until you reach the okay? And to do that, all you need to do is keep track of two things. One is I included, and the other is if I is included or not included, which is the previous problem that you solved. Okay?
So in this case, will it be easier to maintain a separate set where if suppose VI plus OPT is greater, we just add VI to that set and then return and look at that set or less?
So when you say a set, just are you maintaining a single set or is the set indexed by this?
Single set.
Well, a single set, you will end up adding everything, because it's like it's a global variable, and all these things are updating the global variable, so you'll just get everything added.
So we'll only add to the set if
Correct.
that.
But you realize that when you're calculating opt-val IW, for some choice of W, I might want to be included. For some other choice of W, I may not want to be included. So if you're, regardless, you're not looking at it and you're just adding it to just one global variable, you will not get any. Okay. Okay. The running time for this is basically very straightforward. You see that, right? It's n W, n times W. So the running time is theta of n times W. Okay. Okay. So I wanted to quickly go over one other small example, and we will not have the time to cover it completely. So and that has a different structure. So far, all we have done is looked at lists. Okay, there is a list of string characters, a list of items. What if we were given a tree somewhere? Okay. So let's suppose you have a tree with weights on vertices. Okay, this has a weight of 5, this has a weight of 10, 3, 2, 1, 7, 15, 6, 9. Okay, some tree like this. Okay, and a problem that appears often is what is called a vertex cover problem. Okay, a vertex cover is basically a selection of vertices that will make sure that they cover every edge of the graph or the tree. Okay, so you have to select vertices so that it covers every single edge of the graph. What does cover mean? It should be adjacent to, every edge should be adjacent to one of the vertices picked. So for example, one way to build a vertex cover would be, you could pick all the vertices at the odd level. So let's say you pick this vertex and you pick all of these vertices. You agree that every edge is covered. Every edge is adjacent to one of the two endpoints. Okay? So the problem is of finding minimum weight vertex cover. Okay? Problem is finding the minimum weight vertex cover. Okay, so if you want to find the minimum weight vertex cover, you run into basically a similar issue that before. You want to identify is there an optimal substructure property. Okay. So let's say and here when you look you can ask the question from the leaves, you can also ask the question from the root. But let's say I told you that 5 is part of an optimal solution. That particular vertex of, let me call it vertex A. Let's say I told you that A is in the optimal vertex cover. Then what does the remaining problem look like? So if A is part of an optimal solution, what does the remaining problem look like? So you know that you don't have to cover this edge. You don't have to cover this edge. Okay? So what is the remaining problem? Yeah?
Exclude nodes adjacent to it and then repeat it on the rest of the graph.
Okay, so do I remove 10 and 3 or do I just look at this tree and this tree?
We don't consider 10 edges.
Okay.
Then
You don't want to consider 10 and you don't want to consider 3.
yeah.
So let's say pick A, remove this, and you solve the optimal solution for this, and this. Notice the one problem is 10 and 3 may be useful for covering these edges. Okay? So if you remove 3, then when you look at this one doesn't need to have been picked at all, right? Because it doesn't have any edges once you have removed 3. So it's important actually not to remove 10 and 3 And if whatever solution you pick, this takes care of these edges. So we can remove these edges for sure. But the remaining solution has to cover the remaining things. Okay? So if A is part of R, then remaining solution is optimal for the subtrees under A. Okay. What if A is not part of optimal? Then what can you say? So if A is not part of the optimal, that you found out that A is not part of the optimal, then what do you know? You know that 10 has to be included, right, to cover this edge. 3 has to be included to cover this edge. Okay. So if A is not part of optimal, then remaining solution has all of its children. What is the remaining problem once you decide that these, yes?
I have a question. So the problem is we're trying to cover all the vertices, right?
No. Pick the vertices so that you cover all the edges.
Oh.
Okay. So this is not part of the solution. So this has to be included. This has to be included. What's your remaining problem? What is the remaining problem? Yeah.
So the two subtrees under 10-3.
Correct. So the subtrees, so you can remove these edges because this you have to include, so these edges have been covered. So now it is the 4 or the 5 sort of the grand subtrees. Right? The grandchildren. These are the subtrees rooted under the grandchildren. Okay. So if A is not part of the optimal, then the remaining solution has all of its children and contain optimal solution for subtrees rooted in grandchildren. Once you have this, you can convert this into a recurrence relation. This is a different kind of a recurrence relation. This is a recurrence relation built on the structure of the tree, as opposed to on a line or in a sequence of items. But all of this is completely captured. Okay. So for example, you could say opt for a vertex V. This is the root of a tree. This is optimal solution for tree rooted at V. So then you can say opt of V. There are two choices. Either we include V or we don't include V. If you include V, then you will pay the weight of V. But then we decided that the remaining problem is optimal for the subtrees under A. So plus sum over opt of all the children of A, all the children of V. Opt of X, X is child of V. If you decide not to include V, then you have to take all the children of V. Opt of X, X is child of V. And then the remaining is opt of Y, where Y is the grandchild. So this is the recurrence. Okay. I forgot to include the base case. What is the base case? When you have a leaf, what is the weighted vertex cover when there's just a leaf? Do you include it or not?
Parent is included, don't you?
No, leaf is by itself.
No.
There's nothing to do. There are no edges to cover. So you just don't include it. So opt of a leaf is 0. 0 if V is a leaf. Okay, so we'll stop here and we'll do the quiz.